So some alternatives to Bonferroni that you should be aware of are something called the Holm and Hochberg procedures. And these are a little bit less conservative than Bonferroni, but still extremely easy to apply. So this is the way they work. You would take all the p-values from all the tests you run. So if you run 10 tests, then you'd have 10 p-values. You arrange those p-values from the smallest, the most significant, to the largest. One starts from smallest to largest, one starts from largest to smallest. So the Holm procedure says you start with the smallest p-value. So that's the most significant p-value you came up with from all your tests. And you compare it to the Bonferroni p-value. So if you ran 10 tests, that would be 0.05 divided by 10. You would need, so let's say alpha is 0.05, and you ran 10 tests. Then your new cutoff here would be 0.005. That's just your Bonferroni correction. If your smallest p-value is lower than that boundary, then you call that one statistically significant and you keep going. If that one is not, your best p-value of all doesn't make the Bonferroni cutoff, then you have no significant p-values and you stop. But let's say, then that means nothing significant. But let's say that best p-value makes the Bonferroni cutoff. Then you allow the next p-value, you're a little less stringent. You then would say that the next cutoff for statistical significance, we're going to make it a little bit less conservative. So now we're going to compare P2, the next p-value up in significance, to 0.05 divided by 9 rather than 0.05 divided by 10. In other words, your p-value cutoff is a little bit less stringent. If that next highest p-value makes it, it's significant at that level, then you continue to the next step. If not, you stop, and so on and so forth. So this is going to be less conservative than the Bonferroni, because some of the p-values are not going to be compared against that most stringent cutoff level. Now, the Hochberg is the exact same in the reverse. So the Hochberg says start with the largest, the least significant p-value, and compare that to just plain old alpha, just to your 0.05, your uncorrected p-value. If that's significant, everything is significant. So if your worst p-value is still under 0.05, everything will be significant. If it's not significant, then keep going. That one will be called not significant. Now go to the next one down, the next least significant on your list. Compare that to alpha divided by t minus 1. So now we're going to compare that to your original alpha divided by 2 here. And so for the second p-value on the list, you would compare P2, you'd compare that one. So now it's just a little bit less stringent than your original alpha. If that one is significant, all the remaining smaller p-values are significant and you stop there. If not, you got to go on to step 3. And for step 3, you would compare the next least significant p-value to say 0.05 divided by 3. And it gets more and more stringent as you go along. So actually it's going to give you the same answer as the Holm. It just starts with the least significant rather than starting with the most significant. Same idea. Let's just apply this to a practice problem. These are all easier concepts to see with actually in application. So imagine you've got a large randomized trial to compare an experimental drug to 9 other standard drugs for treating motion sickness. And you do some kind of statistical test, an ANOVA test, and it reveals that there's some significant differences between the groups. So an ANOVA test, we're going to talk about this next week, is a global test, and that tells you, well, there's some difference there. Drug 1 is different than something, but it doesn't tell you which groups differ. So then you need to go in and compare drug 1 to all those other drugs. We're going to do 9 tests here. We're going to compare drug 1 to 2, drug 1 to 3, drug 1 to 4, etc. Here's all the p-values that came out of just running what are t-tests, comparing the mean motion sickness in drug 1 to the mean motion sickness in drug 2. We run a t-test, we get a p of 0.05. We do the same thing for the next one, we get a p of 0.3. Which of those differences will be considered statistically significant if we do a multiple comparisons correction? So if you didn't do a multiple comparisons correction, any one that was less than 0.05 would be significant. But that's not correcting for multiple comparisons. So if we apply a Bonferroni or a Holm or a Hochberg here, what do we get? Which ones will come out to be statistically significant? So for the Bonferroni, we did 9 tests, so we divide 0.05 by 9. The new cutoff for statistical significance is 0.0056. Using Bonferroni, then, go back to our list of drugs, the only p-values that came out to be lower than 0.0056 are number 6 and number 9. So only 6 and 9 would be significant. Notice 0.006 here would not be significant, number 7. So according to Bonferroni, only 6 and 9 would be different than the experimental drug. To apply Holm or Hochberg, you're going to arrange the p-values from the lowest to the highest. So the most significant to the least significant. If I apply the Holm correction, then it turns out that 6 is significant, 9 is significant, and 7 is significant, and then everything else after that is not significant. So drugs 6, 9, and 7 become significant according to Holm. If you apply Hochberg, again, you're applying it in the other direction. It's actually a little bit, takes you a little bit longer here, but you find out that 7, 9, and 6, the same 3, are significantly different. And again, just by looking at these procedures, you can see how they're applied. You'll notice that Holm and Hochberg are less conservative because additionally, drug 7 comes out to be statistically significant in those cases. It's good to be less conservative because you end up with, if it's appropriate, because you end up with more things coming out statistically significant. Again, Bonferroni is only appropriate if everything is independent, which is usually not the case. If everything is not independent, Bonferroni is too conservative and you're going to miss a statistically significant effect that you should have found. In other words, you're going to make a type 2 error.